All right, so hello everybody and welcome. For those of you who don't know me, my name is Gertina Bessel. I'm a professor in the Astronomy Department and chair of the TAP program. I love this event. This is great because I love listening to the amazing grad students across our three departments, planetary science, astronomy, and physics, and hearing all the things that they're doing and realizing that the connecting thread between all of us is theory, right? The tools that we use and our approaches towards solving some of the most fundamental questions in science in our respective disciplines. So we have an amazing lineup today, and we'll go through everyone soon enough. And I wanted to highlight a few more things about the TAP program. And the first one is that we have a research prize that goes to a graduate student who has submitted a paper recently that has made a profound impact on the field. And you can apply for this at any point in time in your career. And if you have a paper that you think has made an important impact. And this year's winner is Soleil Hyman in the Astronomy Department. Congratulations. Novel code Peccary to characterize orbital complexity, stochasticity, and regularity. And she's the expert in chaos if you have any questions about it. I also wanted to highlight the TAP travel grant. And so this is really important. Students are always asking, how do you get the top postdocs in the country? How do you become a faculty member? The way you do this is by giving talks and getting your science out there and getting your name out there. And that's something that you actually can control. You can control where you go to give talks. We're trying to provide you with up to $1,000 each to go and give you funding to go and do that, right? These don't have to be at conferences. They could be workshops. They could be presentations you're giving at a department to a group that you know is going to be working in the area that you want to work in, or maybe even a place you want to go as a postdoc. So pay attention to these deadlines that are there for all students doing theoretical work, regardless of whether it's planetary science, geology, astronomy, physics. Okay, so we are going to get started. There is a sheet that's going around. Please make sure you've signed in and make sure that gets passed up to the front. And I will let Mathieu explain how the rest of this will go.
Yes.
And then,
Yeah, I probably don't need that. I'll switch. Yeah, so hi everyone. I'm Mathieu Lance. I'm also in the Astronomy Department. I'll be chairing the talks from these 6 people. Everyone gets 5 minutes, no, that's 7 minutes, excluding questions. Yeah, 7 minutes to talk and then question time. And
will you be giving them a warning?
Yes, I can give you a warning after, like when you're at 2 minutes left. I'll wait or do something, try to catch your attention. And so the first speaker is Namya Baijal.
So advance, the green one is your laser pointer on each. And then stand over to the that side, and that way.
Sure. Okay, perfect. Well, hello everyone. I'm Namya Baijal. I'm a PhD candidate at LPL, and today I'm going to be talking to you guys about the collisional modification of asteroid 16 Psyche and the effect of pre-impact rotation. So asteroid 16 Psyche is a metal-rich asteroid, and it's one of the 25 most massive asteroids in the main belt. Here I'm showing an example of a couple of those asteroids from Bernas et al. 2021. Psyche's down there. So looking at a plot of bulk density on the x-axis and rotation rate on the y-axis per day, we can see that these 25 most massive asteroids kind of plot across that range. Here, the circles represent the different taxonomic types in different colors, and the sizes are scaled with the log of the mass. And we can see that Psyche kind of plots to the highest bulk density range and also has the highest rotation rate of these largest asteroids as well. Now, Psyche's rapid rotation rate is not something that's very unique to metal-rich asteroids. Looking at a similar plot of asteroid diameter on the x-axis and rotation rate on the y-axis, we can see up there that Psyche is, kind of in that cluster of the rapid rotation rate that we see. And this is sort of a consistent pattern where metal-rich asteroids seem to have a rapid rotation rate between 5 to 10 hours. Now, we think that these metal-rich asteroids may be the remnants of metal cores which lost their rocky mantles as a result of a giant impact. So here I'm going to show you guys a movie where we have 2 similarly sized bodies colliding at nearly head-on angles. And as this plays through, you can see that the target here loses most of its rocky mantle, which is represented in blue, leaving behind a body which is predominantly metal-rich, represented by that pinky material. And we think that such a process causes the production of these metal-rich asteroids, and Psyche may be one of these. Now, what we can do is model the formation of these impact basins on the surface of these asteroids to understand not only their surfaces, but also their interior structure. And similar studies have been done in the past for asteroid 4 Vesta, as plotted on the left. And the reason why we think Psyche is such a great candidate for this study is because A, there's a NASA mission going to that asteroid, which is set to arrive in 2029. And Psyche, we think, is composed of 30 to 60% volume metal. And it has these impact basins on its surface, as you can see, which is we know from the shape model of the asteroid. And so we think it's a good candidate to be able to study these processes. Now, what we do is we use the SPH, which is a smooth particle hydrodynamics code. This is quite different to the SPH models that you might have seen for, sort of galaxy or star simulations, because here we have to think about the rock mechanics. And to do so, we use something known as a P-alpha porosity model, where porosity is represented as distension. And we have recently shown in a paper which was just accepted that the porosity plays an important role in not just the cratering physics, but also in the final distribution of rock and metal across Psyche's surface. So we incorporate these things into our model, mapping the effects of material strength and also solid friction. We use the realistic asteroid shapes, which is also something that we get from adaptive optics and radar data. And then finally, we developed a new equation of state using Tillotson, where we modeled the interior composition of Psyche using a stony iron interior, from which we derived this from laboratory experiments and then put this into our model. Now, in this study, we simulate the formation of a north polar crater, which is approximately 50 kilometers across. And then we also model an equatorial crater, which is approximately 100 kilometers across. We do these impacts in the prograde as well as in the retrograde directions. We use a 10% porous interior for Psyche with a 5 kilometer per second impact speed, which is reflective of the average collisional velocity of the main belt. We use 4 to 8 kilometer radius impactors depending on the basin that we're trying to produce. And then finally, we use a 4-hour rotation rate for Psyche, which is reflective of its modern day value. Now, moving on to the results, I'm about to show you a movie on the left, which is of a Psyche which is not rotating. And on the right, we're going to look at a Psyche that's rotating. We're looking at it top down to show you the formation of the polar basin. And the pink represents our target material and the purple, the impactor. And as you guys can see, with the influence of rotation, we get these sort of very asymmetric ejecta patterns. And this is similar to what's been observed on other asteroids as well. So this is something that the mission may be able to observe when we get there. And we also find that the effect of rotation significantly increases how much impactor material gets preserved on the surface of the asteroid as well. We also find that it's not just the effect of rotation, but impact angle, which also plays a significant role in this process. So on the left, we're looking at a prograde impactor, which is coming in at the same direction of rotation as Psyche. And then on the right, we're looking at a retrograde impact. Now, in these cases as well, we can see these sort of very asymmetric ejecta patterns, but one of the main findings that we see is that when the impact happens in the prograde direction, we preserve almost 1.5 times more of impactor material across Psyche's surface. So it's sort of the coupled effect of impact angle and rotation, which is at play here. We can look at these impacts in 3D as well to show you the sort of global distribution of that impactor material. And that asymmetric pattern where we get material from the pole preserved all the way down to the equator and to the other side of Psyche as well. And this shows you a little bit more visually that the prograde impacts are more efficient in producing more impactor retention. This effect is not just observed at the poles, but we see this in the equatorial region as well. So here we're looking at that equatorial impact with rotation, and we're also looking at that prograde impact. So this is also helping enhance sort of material retention as well. So asteroid 16 Psyche is a metal-rich asteroid, and it's a fast rotator amongst the 25 most massive asteroids, and this is not unique to metal-rich asteroids as well. We modeled the formation of the large basins on Psyche to be able to understand its collisional history and how rotation plays a role in this. We find that targets which have pre-impact rotation tend to retain a lot more of that ejecta, not just at the poles and the equator, but across other latitudes as well, which is something we're currently investigating. And this effect is enhanced when the impact is prograde. In future work, we want to estimate the overall contamination fraction from these impacts to be able to compare it with spectral observations from Psyche's surface to be able to estimate how much of that exogenous material was delivered. And finally, this can be compared with observational data once the mission actually arrives in 2029. Thank you, and I'll take any questions.
Questions? A few questions.
Sure.
Maybe the first one that is most relevant is, what's the kind of lifetime of the surface of the asteroid? Because the starting point is the impact parameter, so I assume there must be a limit on how far back in time you can go.
Right, exactly. So these impacts assume that, you know, there's not sort of like we're not going as back as the formation, but we assume that Psyche is formed at this point, but we don't put it at a particular place in time. So we assume that any time after, you know, the sort of 4.5 billion years of solar system history, this impact took place. And then what we can do is that we can extrapolate over time to see how much of this material that was delivered to Psyche and sort of extrapolate that contamination fraction, which is sort of the second part of this study. And then we can kind of provide a number of how much exogenous material was delivered and then compare it with spectral data that's already out there.
Apologies if you said this, but how frequent are these impacts?
Okay, so so in terms of frequency of these large impacts, they're very rare, right? So Psyche probably got hit with maybe 4 or 5 sort of big impacts in its whole like sort of lifetime, and we know that because we see these large depressions on its surface. But once we get there, we are likely, and kind of compared to what we know from other asteroids, we're probably going to find smaller impacts which are going to be at a higher frequency.
So you're making predictions for a mission that's actually going to happen. And so how are you working with, so talking as a theorist, how do you communicate with the instrumentation team or the team?
Right, yeah, and that's honestly the most exciting part about this research, because I get to be a student collaborator on the mission. So far my research has been kind of entirely theoretical, where I've presented these models to the team, and there's sort of different working groups. So the working group that I've most closely been associated with is the impacts working group, and they're going to map a lot of these surface craters. But what I hope to see out of this is maybe from these models we could compare it to like gravity data, as well as sort of like the multispectral imager, which is going to be able to see a lot of this, and then hopefully be able to make some predictions about, you know, the surface of Psyche, but also what its interior is made up of.
One last question here.
I think this is a quick question. In your simulations, in the visuals, it seems like none of the asteroid, the target material is being knocked off. Is that because you don't allow that in your simulations, or it just doesn't happen because of the properties of your target?
So it actually, we do see target material in, I think probably this is just the way that I've plotted it with composition, but it's a little bit clearer. So here I'm plotting it as a function of porosity. And the target material is ejected, but most of that kind of remains in the vicinity of the crater, so it's a little bit harder to see. But in terms of like the amount of material, it's mostly the impactor that we see really making its way across the surface of Psyche.
Well, let's thank our speaker again. Thank you. This Niranjana. I'll meet you on 5 minutes.
That would get us nowhere.
Okay. Hi everyone. I am Maria. I'm a 6-year PhD student here. I work at Stewart Observatory among the many astronomers there. But I think it's pretty clear that I hail from the physics department, because one of my favorite questions to ask in my research is, what about magnetic fields? And this goes especially for objects that are rotating. And there's a lot of really cool places where these are actually super important and relevant. One of those is neutron stars. We have some of the largest magnetic fields in the universe there, often rotating, and some of you might be interested in many of these phenomena associated with a neutron star, and specifically its magnetic fields. And one thing that I want to emphasize about neutron stars, and really all the objects and scenarios I'm going to talk about, is that we don't have a great idea what those magnetic fields look like right now. We don't even know for neutron stars really what magnetic fields look stable. We don't have a great idea of what magnetic fields can be stable in neutron stars, let alone what magnetic fields are actually likely to be there if you think about the formation history of the neutron star. And so if I had time, I would tell you about these how this impacts for any observers in the audience. This is pulse profile modeling and gamma ray burst afterglows. Feel free to ask me about it after this. But moving on to the next object that I'm interested in, core collapse supernovae and magnetic fields in those. So one of the obvious reasons that these are important are because they connect to the formation of neutron stars. They're the birthplace of most neutron stars. And so this is going to give us information about the formation of the neutron star and its magnetic fields. But magnetic fields are also relevant to a lot of phenomena that happen within the core collapse supernova itself. They're going to have a significant impact on explosion energy and explodability, aspects of the ejecta, and various multi-messenger signals that we might see from the core collapse supernova. So they connect to that end state of the protoneutron star, but they're also relevant to the supernova itself. And this brings us to the question of what about magnetic fields in pre-supernova models? And by pre-supernova, I mean stars that are like tens of minutes away from core collapse. So they've gone through most of their lifetime, they've reached the end of their life. The core is contracting, but it's not quite ready to collapse yet. We have late stage burning in the outer shells. And you might think that we know the most about magnetic fields around here and that we're just struggling to propagate it through to these other stages. It's the opposite. We have some of the least information about magnetic fields at this stage, and pretty much at every stage, when we look at it and when people tend to model it with magnetic fields, we just slap a field on there with no idea whether it's a well-motivated place to start. And so these are important to look at, but only a handful of studies so far have looked in 3D at either magnetic fields or rotation in late stage burning, and actually only one has looked at magnetic fields and rotation in the same model. These are some of the details I'm going to leave up here for those who are interested. But what I want to emphasize is that magnetic fields and rotation are not something that you can treat separately and then just hope to add together afterward. Say we know the effect of the magnetic field, we know the effect of rotation, we'll put those together, and that's what happens in a rotating magnetized model. Rotating magnetic fields are their own beast. We have magnetic fields winding up because of the rotation and reconnecting. We have the magnetic fields impacting the angular momentum transport. And if you have convection, you also have that to contend with, which you do in most of these late massive star models. And so it's really not enough to model them separately. We need to do it together, and we've barely done that so far. And so that's where my current work comes in. Right now, I'm working on modeling pre-supernova models in full 3D with magnetic fields and rotation. And so what I'm doing is taking a core collapse supernova progenitor that I've generated in MESA, which is an open source 1D stellar evolution code. I follow it almost all the way till core collapse, and then about 10 minutes before, and I give it an average rotation. I'm looking for what most of the progenitors we expect to see are going to look like, not one of the edge cases. The other study also was rapid rotation, which is interesting, but not what we expect to see in most of the core collapse supernova progenitors. And so I'm mapping that into a 3D MHD code about 10 minutes prior to collapse, and initializing it with a range of different magnetic fields and one model with no magnetic field, so that we can compare those models, see what impacts magnetic fields are having, and also compare this to the previous study, because if you were looking at the stats on the previous one, you will notice there's some crude approximations, and we're not necessarily sure if those are good enough to capture the relevant effects of the magnetic fields in these models. So hopefully these simulations are starting almost any week now, and we're going to learn about how the 3D magnetic field structure in pre-supernova stars impacts the stellar structure, convection and rotation, nuclear burning, and then, of course, how that magnetic field is evolving with all these things, and whether specific instabilities and dynamos are contributing to the evolution of that magnetic field. And, of course, looking at the previous study, seeing whether the approximations it made are really accurate, or whether we need something better moving forward in future studies. And this, hopefully if I click it, it's going to play. This is a sort of preview. This is not the results. Okay, I took an old MESA model from one of my advisor's old papers, and I just ran a test to see what we can expect our outputs to maybe look like. So yes, here we go. So you're seeing the oxygen shell of the star, and then inside you see, actually I wonder if I can go back. There we go. So this yellow and blue area is the oxygen shell. We have different concentrations of silicon to trace the burning of the oxygen in the shell. The pinkish red in the center is the iron core of the star, and then you can see these magnetic field lines colored by their strength. This is a model with a dipole magnetic field. And if we let it play, you can see those magnetic fields winding up in the center and getting all tangled by the convection in the oxygen shell. And this model is, you're seeing about 600 seconds of evolution in total, a little bit less. And so we're going to see a different version of this this is also a rapidly rotating model. So we want to look at a more average rotation model and with updated features from our MESA models. But once we have this, there's also a lot of interesting fusion to take it in. Obviously, we can test a much wider range of initial magnetic fields because we need to know if we're just getting out what we put in or what kind of function what we get out is of what we put in. Since we also don't have that much information about the magnetic field, obviously in a 1D code, there's a lot of limitations on how much you can follow those magnetic fields all the way up to this stage. We can also use these models to initialize core collapse simulations. Most core collapse simulations right now start straight from a 1D model. They slap it in there, map it into 3D, and then usually take some like perturbations and put those in there just to try and make it a little more realistic, because we know that that spherical symmetry is probably unrealistic for the progenitors of the core collapse supernova, but we can actually take these models and directly do core collapse simulations with them to see what this realistic structure will do to the ensuing core collapse supernova. And we can explore a much wider range of initial progenitors, including specific channels for things like formation of magnetars. I can talk lots more about that, but I'm going to let this, I have a questions and thank you for listening slide, but I think I'm just going to let this play for you while I do that.
I have one question that you touched upon, like the sensitivity to initial conditions. Like
Yes.
from this movie from Carl, it looked like the initial conditions were a dipole.
Yes.
But this is 10 minutes before the supernova, so 10 million years after the evolution. And if you assume that the Spirit-Taylor dynamo is what transports angular momentum, you should probably expect a very poloidal field to begin
Yes.
with, instead of a toroidal one, and instead of a dipole like this. Do you think that, like, what are the initial conditions that you're taking in magnetic fields, and what is the impact?
So we're looking at exactly how many different models we can start with. The dipole model is kind of ready to go, although this one is much closer in than we actually would necessarily start with. This is a very compact dipole. We're also looking at a quadrupolar model really to understand how higher multipoles affect the angular momentum transport at like the equator. And I'd really like to see an initial randomized small scale field to understand.
Yeah, because I think that's what the Spirit-Taylor dynamo would actually predict.
Exactly.
Right? So you would have a very small magnetic field, basically seed perturbation with a geometry that we don't know very well, but probably dominated by toroidal components.
Yes.
But yeah, okay, that's great. Thank you. Vikram.
Maria, what are the prospects for confirming? What's the best possible outcome? Like, will you find a standard like magnetic field that the star falls into, or is it about finding, is there enough magnetic field at death to support jets and stuff like?
So there are interesting implications for whether it supports a fossil field model, so like a progenitor, or whether we really expect most of the magnetic field to be generated during the core collapse supernova through continued dynamo. We can't really answer that without going through the supernova phase itself, but there's also, I guess, from a perspective of being able to like study this a lot more and in greater detail, it would actually be awesome if it turned out that the previous studies, like kind of crude approximations, do work pretty well, because then we don't have to worry, like if no matter what initial model you put in, you're getting similar things out, then we can say, okay, it's the process that matters, not the initial field that we put in, and then we can kind of put in whatever we want or need to that suits our computational methods. And so that would be cool. I don't know if that's going to happen. I'm skeptical of that, but that would be great, because then it's quicker and easier to run more of these, and we know that we're not just getting out what we put in, right? We're getting out something that has to do fundamentally with the physics of what goes on in these tens of minutes. Yeah.
A great talk. I was wondering if you could get some intuition on what do you expect to get out of observation of things like radio pulsars or things like that, or things, because for this kind of processes, then both the magnetic field and the spin would be pretty important. So you think we'll be able to decouple them and basically from your progenitors know like what you need to kind of put around the initial condition from these kind of observations?
Sorry, I'm trying to understand. Your question is if we can get intuition from this, like what?
The other way around. Like,
Mhm.
can you get like some sort of intuition of what are the magnetic field you would expect, at least like after the explosion, from the observations of radio pulsars to understand the initial configurations you want to put in your models?
That's an interesting question. I guess I've looked at it. There's definitely some models suggesting that like the strength of the magnetic field doesn't necessarily matter as much. Potentially the shape is less well known, but that when you go through core collapse, you kind of get rid of any memory you had of how strong it was beforehand, and you're more just at that the strength is being generated in the core collapse. And so I don't know if you could necessarily get specific information through that, because that's almost telling you that, again, like it doesn't matter as much, that particular aspect of what goes into what comes out. But yeah, theoretically, if you run enough initial models and you say, okay, every time we start with this, we're ending with things like this, and these are what we're seeing in pulsars, then maybe we can go backwards and say, okay, then it's probably these ones that we're starting with more often. That'd be cool. Yeah.
In the interest of time, we should thank Maria again. The next speaker is Himansh Rathore.
Great. Hi everyone, my name is Himansh Rathore. I'm a fourth year astronomy PhD student here at Tesla. And today I'm going to talk to you about our Milky Way's two most prominent satellite galaxies, the LMC and the SMC. So collectively known as the clouds, the LMC and the SMC are prominently visible from the southern hemisphere. And I'm going to tell you what these galaxies teach us about the processes that govern galaxy evolution. My focus will be on the smaller of the two clouds in particular, that is the SMC. So when we talk about galaxy evolution, it turns out that collisions between galaxies are a major driver behind galaxy evolution. Collisions are a ubiquitous phenomenon in the universe, happen all the time. And collisions, they govern how galaxies transform into the present day morphologies and kinematics that we see when we look up in the sky. And excitingly, with the LMC-SMC system, we have a great opportunity to understand the physics of galaxy collisions in unprecedented detail, thanks to telescopes like Gaia and Hubble. So Gaia and Hubble have given us 3D velocity vectors of these satellite galaxies, the LMC and the SMC. And these 3D velocity vectors suggest that the LMC and the SMC have recently collided. This collision happened less than 200 million years ago, which is a blink of an eye in galaxy evolution timescales. And here the impact parameter of this collision was such that the SMC crashed through the LMC's disk. And given the proximity of this colliding system, as an observational community, we have spent tremendous amounts of resources observing the LMC and the SMC. And this includes ground-based telescopes, space-based telescopes across the electromagnetic spectrum, and a lot more is to come in the future. And we have collected a wealth of observational data. So we have the internal velocity fields of the stars that constitute the LMC and the SMC. We have resolved stellar photometry across a variety of stellar types. And we have precise maps of a variety of tracers of gas and dust in the LMC and the SMC. If you are intimidated by this slide, I have served my purpose. But what has all this observational data given us? Different people will have different takes on this. In my humble opinion, with all this observational data, we have only achieved confusion. And theoretical models of the LMC and the SMC, particularly the recent collision, are required to address some of the problems that the clouds are raining down at us and interpret all of this observational data. So let's look at those problems. Problem number one. This is how the SMC's internal stellar velocity field looks like. By the way, this is a remarkable measurement. Credits to the Gaia telescope. These motions are of the order of milliarc seconds per year on the sky, which means these stars move by an angle of 1 degree in 4 million years. It is amazing that instruments like Gaia can resolve this motion in a mission lifetime of 10 to 15 years. It's clearly an era of precision astronomy that we are in. But anyways, you can see that in the SMC, there's not much of a stellar rotation going on in here. Most of the stars are in fact moving away from each other. Now, this is inconsistent with the amount of gas the SMC has. The SMC is very gas-rich. It has more gas than stars. And when you have a very gas-rich system, think of a protoplanetary disk, things tend to settle into a nice rotating configuration. Why is this not happening with the SMC? So our hypothesis is that it is the LMC-SMC collision that has something to do with this. And we use the LMC-SMC hydrodynamic simulations, which were performed by my advisor, to understand how the SMC's kinematics evolved during a collision with the SMC. This is supposed to be a movie which is not playing. Imagine a simulation between the SMC and the LMC. The SMC goes up and comes crashing down the LMC's disk. All right, so this is the observed picture of stellar rotation that we are trying to explain. This is how the SMC stellar rotation field looks like prior to the collision. You can see nice coherent rotation going on here. And after the collision, this is what happens. So most of these stars after the collision are now moving away from each other in the SMC, which is a picture that is consistent with the observation. And it's the LMC's tides that act to disrupt the SMC's stellar rotation, making the clouds an important testbed for gravitational dynamics and colliding galaxies. Problem number one, solved. Problem number two, this is how the SMC looks like on sky. This is just a simple iridescent map of the stars. And this point here represents the stellar center. Now, if you were to mark the location of the gas center on this plot, you would realize it lies all the way towards the top left. The stellar and the gas centers are separated by more than 1 degree. This is a big problem because this galaxy is barely a few degrees in extent. So how do you get the stars and the gas to be so separated from each other in a galaxy that is already so small? The answer lies in hydrodynamics. So when the SMC collides with the LMC, the SMC's stars only face the gravitational forces. But the gas, in addition to facing the gravitational forces, also faces the hydrodynamic forces. And here, a particular hydrodynamic force that plays a role is ram pressure. So ram pressure is the same force that causes water droplets on your hand to fall off as you move a wet hand across the air. And it is this balance between the hydrodynamic forces and the gravitational forces that set the final configuration of the SMC's gas in this collision. And that consequently explains why the SMC's gas is separated from the stars by so much. And this makes the clouds an important testbed for understanding hydrodynamic processes in galaxy collisions. So just to conclude, I would say that the observational data of these two galaxies is just way too rich. And the problems that we have are also way too rich. And we really need state-of-the-art simulations of the LMC-SMC Milky Way interaction history to solve these problems, interpret all of this observational data, and utilize the clouds as the next generation astrophysical laboratory. So for my thesis, I'm developing these high-resolution N-body simulations of the LMC-SMC Milky Way interaction history. I call these the mega simulations. Mega is the Sanskrit word for clouds. And we have 30 million particles in total. This is really state-of-the-art. This is supposed to be a movie. Imagine a really state-of-the-art simulation of the LMC-SMC. Some epic stuff going on in here. And the development of the simulation is thanks to the amazing HPC facilities that we have here, the HPC staff, and also the TAP program. Audra, I don't know if you're listening to it, but thank you so much for tirelessly working to ensure that such research is possible. So that's all. Thank you so much for your attention. I would be happy to take any questions. Questions?
Hi, Himansh. This is really cool work. We like to use the LMC and SMC as a great test case for other galaxies, especially in the early universe. Have you thought about how the mass ratio between the SMC and LMC might change what we see?
So just to understand your question, like if the LMC and the SMC were a different mass ratio, how would that change the observables?
Especially since if we want to use the LMC and SMC to model other galaxy interactions early in the universe, I imagine there would be a wider range of mass ratios.
Certainly. So yes, in general, when you look at galaxy interactions, the range of mass ratios that you get are pretty diverse. You get like almost major mergers in which the mass ratio is 1:1, and you get these 1:10 mass ratio galaxy mergers and so on. So I think the LMC SMC galaxies can teach us a lot about 1:10 mass ratio galaxy mergers and mass ratios that are in the vicinity of that. But major mergers, maybe not so much. But on that note, 1:10 mass ratio mergers and ratios in the vicinity of that are actually very common, especially in the high redshift context. So still, the system is quite widely applicable, if not for all cases.
What's the time scale for the gas center mass and star center mass to line up again?
Great question. So, if there were no external tidal influences present, and if you just leave that configuration of gas and stars together, I would expect both of them to line up in a dynamical timescale, which for the SMC is approximately 100 million years. But the thing is, such a collision happened less than 200 million years ago, which is of the order of a dynamical timescale. So the system has not had enough time to be in equilibrium, and it is unclear if it will ever be in equilibrium.
So I have read some works on the Magellanic Bridge connecting the LMC and the SMC, and there are some like very metal poor stars there. So does your like simulations of a collision between LMC and SMC also naturally create a bridge like that, where you can have these like really metal poor stars forming there?
So you're talking about the formation of bridge and how you get the metal poor stars in there? Yes. So the bridge is a natural product of such a collision. In fact, during the collision, when the SMC collides with the LMC's tides pull up some of the SMC stellar material into the bridge, and you get the stellar bridge. And the SMC is significantly metal poor compared to both the LMC and the Milky Way. So the origin of the metal poor stars in the observed LMC-SMC bridge is likely because during the collision, some of the metal poor stars from the SMC's main body were removed to form the bridge.
Last quick question.
Well, I'm always getting the last question. My question is also about the timescale. And I'm wondering why you characterized 200 million years as a blink of an eye when the total age is, maybe 10, 50 times as much, right? The universe is maybe 50 times older than 200 million years. So why is 200 million years a blink of an eye? It's a dynamical timescale.
Yes. So when I said the blink, so the meaning of when I said the blink of an eye, that's in the context of how long galaxies typically take for their morphologies and kinematics to significantly transform. And that is usually of the order of few billion years. And that is the standard picture that we have. And
that's 10 times as long, let's say.
Yes, I guess we have different definitions of what a blink of an eye is in the galactic community and the planet. But I guess the point of what I'm trying to show here is that the standard assumption that galaxies take billions of years to evolve, that no longer holds when you have close interactions, and you can transform galactic morphologies and kinematics significantly within a few dynamical timescales, which is a blink of an eye.
What's astonishing to me is that you get these morphologies in just 10 dynamical timescales. That's astonishing.
Indeed.
Okay, let's thank Himansh again. Oh, 40 minutes to 1, there are 5 minutes.
Oh, wait, let us play.
That's the SMC. That could be an interesting variation, presenting the talk of other people. Thank you.
Okay, back from galaxies to stars. So my name is Neev. I'm a graduate student at Asteroid. I work with Matthew. And today I'll talk about some of my work that was just on the archive today. So in 2015, we detected gravitational waves from merging black holes for the first time, but that was just the beginning. Since then, detecting them has become routine. And it's an exciting time to be in this field because this catalog is only going to grow exponentially in the coming years. And we are now in like the era of gravitational wave astrophysics. Here I'm showing all the detected events till now. It's about 200 of them, and the masses of the emerging black holes and neutron stars on the y-axis. And now we can study all of these events as a population and try to answer questions about how did these black holes or neutron stars end up merging in a binary. But with a great catalog comes the even greater problem of finding a number of outlier events that do not fit in well with the rest of your population. And this number is only going to increase as the catalog size increases. And in my biased opinion, the flag bearer for an outlier gravitational wave event is GW19814 from 6 years back, which was the merger of a 23 solar mass black hole merging with a tiny 2.6 solar mass compact object where we don't know whether it's a neutron star or a black hole. And the question that arises is this event weird in some way that it does not fit in well with the rest of the population, given it is the most unequal mass ratio event to date? And do we need some exotic explanations for it? And in the next 5 minutes, I hope to convince you that it's maybe not that weird from an astrophysical point of view. But to do that, I will first take a step back in the standard path to forming a gravitational wave source, where you start from two massive stars that go through a tough life together, and only a small fraction of them end up in a gravitational wave source. And only the last part is what the gravitational wave detectors detect. But many of these intermediate stages are something that we observe in our own galaxy. And especially one of the phases is the high mass X-ray binary phase that happens after the formation of the first compact object. And given the unequal masses that we see in 19814, a question that we can ask is, what is the most unequal mass X-ray binary that we know of? Turns out we've known this system since the 1970s, which is this high mass X-ray binary with this phone number. And it's the most unequal mass system that we know of in the galaxy in the X-ray binary population. And the good thing about being in the galaxy is that we can study the system extremely well with our telescopes. For example, we know it's a 2 solar mass compact object that's accreting from the wind of a massive 45 solar mass star in a tight orbit. We have kinematic information for the system thanks to Gaia. And we also know about its local environment, such as the age and its parent cluster. This is useful because now we can do Monte Carlo simulations and try to reconstruct what the system looked like just before the supernova that formed the compact object. And we can get many constraints, such as what was the mass of the progenitor that formed the compact object, and what was the orbital period of the system just before the supernova. Now with this, we can use a stellar evolution code like MESA to construct detailed binary evolution models and try to reconstruct the formation history of this X-ray binary. And what we find is that if mass transfer is conservative, that is the accretor gains most of the mass from the donor, we are able to reproduce most of the properties of this X-ray binary very well and also reproduce its position on the HR diagram today. Now, in the future, when the star grows, it's going to fill its Roche lobe and mass transfer is going to get unstable. And the compact object is going to get engulfed in the envelope of the star. But since the star is still on the main sequence, its envelope is very tightly bound, and there is not sufficient orbital energy in the system to eject the envelope. And we believe that the system is likely going to prematurely merge and not form a gravitational wave source. That's the merger of two compact objects instead. But to form a gravitational wave source in a very similar way, we just need to do something a little different. So to explain the formation of GW19814, I once again compute detailed binary evolution models, but now at a lower metallicity, because gravitational wave sources usually formed when the universe was much younger and metal poor. And we again find that mass transfer is conservative, which helps to invert the mass ratio of the binary significantly. But now the key difference is that when the lower mass compact object forms in a supernova, the separation of the binary after the explosion sensitively depends on what is the natal kick that this compact object receives. And that is what decides the fate of the system. So once the star again fills its Roche lobe, it's again going to be a common envelope phase, and the fate of this phase depends on what's the binding energy of the star at the onset of common envelope. And what we find is that when the size of the star is small at the onset of common envelope, the binding energy is too high and it's likely again going to lead to a premature merger, like in the case of the X-ray binary. But on the other hand, when the star is large enough, its binding energy decreases drastically, and there can be a successful common envelope phase where the system is able to eject its envelope and you would be left behind with a tight binary in the end. And what I find is that this occurs when the star is on the red supergiant branch, where it develops a thin, loosely bound convective envelope that's easier to eject. Now, after the common envelope phase, the binary shrinks significantly, and you would be left behind with the core of the star that lost its envelope with its compact companion. And this core is about 20 solar masses, which is too massive to explode. So this core will likely implode and form a 20 solar mass black hole. And then these two compact objects would in spiral and merge in a gravitational wave event that would be very unequal in mass and will look very similar to GW19 or 814. Not just that, we can go a step further and use the fact that there are just two unequal mass, high mass X-ray binaries that we know of in our own galaxy, and use that as an information to try to estimate what's the rate of unequal mass gravitational wave events that LIGO would see. And with some back of the envelope calculations, I was able to show that our observed rate matches very well with the rate that LIGO finds for such kinds of events. So to summarize, I hope I was able to convince to you that GW190814 is not that weird from a binary evolution point of view. And in future surveys, we're going to find many intermediate stages of massive binary evolution in our own galaxy that provide a wealth of information, which we can use as a bridge to understand the gravitational wave sources that are being detected by LIGO. Thank you.
It's a great talk. So, have we observed some high mass X-ray binaries, and can any of the high mass X-ray binaries that we have actually observed could be possible progenitors of such gravitational wave events?
So that's a great question. So the question is, are any of the high mass X-ray binaries that we have observed, can they form a gravitational wave source? The answer is mostly, I would say no, but it really depends, because most of the high mass X-ray binaries that we know of consist of like a massive star with a neutron star companion, and the star is not large in size, so it doesn't have a loosely bound envelope, and most of them are going to just lead to a premature merger, which can form something that's not a gravitational wave, but like something like a Thorne-Zitka object, which will have a neutron star that's embedded in the star, which is not a gravitational wave source that LIGO detects, but that's the fate that's predicted for most of the high mass X-ray binaries in our own galaxy, although there might be some edge cases.
Sorry, I think I missed this. What was the role of metallicity in the outcome of this binary?
So the role of metallicity is that the X-ray binary is in the galaxy, so that's why we use solar metallicity. And gravitational wave sources, at least from the detections, we cannot say what the metallicity of the binary that formed the event is. But generally, people tend to study these things at lower metallicity because formation of black holes, like a massive 23 solar mass black hole, is more efficient at lower metallicity. But the same thing could be, let me go back. I could do the same calculation at higher metallicity. It's just the fate of the system might be different. But for a gravitational wave source, I chose to do it at a lower metallicity because that's the more relevant case for the events that we are detecting today. Because it takes time for the merger to occur. And so the system formed when the universe was much younger and likely more metal poor.
Do you have any intuition for how it would change the outcome?
So if metallicity is changed, like the most important role of metallicity is stellar winds. So at higher metallicities, stars lose more mass through winds, and the final remnant might be less massive. So it might be possible that you will never be able to form a very massive black hole that's like 20 to 30 solar masses at solar metallicity, but you can do that at lower metallicity because winds are become much weaker. So the star doesn't lose that much mass.
You know the slide with the probabilities or the rates?
Oh.
I'm just curious what like basic assumptions, you said this is the back of the envelope.
Yeah,
calculation,
yeah,
and going into these rates.
So the question is, how did I get these rates in the first place? This is very back of the envelope. I did not. For a detailed study, you need to do a population synthesis simulation where you simulate many binaries and look at their fates. Over here, what I did is I assumed like what's a reasonable natal kick distribution that compact objects get, and what would be the, and given the distribution, what would be the possible sizes of the orbit per supernova. And given that in my simulations, I was finding that you can only from a gravitational wave source when the star is very large, which is like somewhere around 1,000 to 2,000 solar radii. That's what I classify as a gravitational wave source. But everything that's less than that, the star will do mass transfer when its envelope is more tightly bound, and it will be visible as a high mass X-ray binary, but its final fate would not be a gravitational wave source. So I just find the number of systems that are in that range and the number of systems that are in this range. And given that we see two in the Milky Way that correspond to that range, I sort of divide that number to get a rate for gravitational wave events. It's very back of the envelope, and this is not the most latest version of the plot. So
Or doesn't say. Okay, let's take Neev. And next is Niranjana.
let me just go to my backup slides.
Wow, you had a few backup slides. I'll wait with you when you're 5.
I am Niranjana, and in this talk we'll transition to something that is very close to us, which is the sun and the solar wind. So a solar wind is a continuous stream of charged particles that are emitted at the surface of the sun and they expand out. And the solar wind, along with the magnetic fields that extend out from the sun, exist in the space around the sun called the heliosphere. The solar wind is continuously heated as it expands away from the sun. So in the plot here, the black curve is the observed temperature profile of the solar wind as a function of radial distance from the sun. The green curve is the expected temperature profile for an adiabatic expansion. So we see that the black curve is consistently higher than the green curve, so which implies significant heating. So we want to understand this heating of the solar wind to understand the solar wind itself. And this heating is not due to conventional heating processes like conduction or convection or radiative heating. It's due to dissipation of turbulence in the solar wind. But why is there turbulence in the solar wind? So there are these convection cells inside the sun and the plasma is moving. And because of this, the plasma on the surface of the sun keeps moving continuously. And this causes stirring and generate waves called alpha waves in the magnetic fields that extend out from the sun. So alpha waves are characterized by transverse magnetic field perturbations. And they propagate out, and some of them can get reflected back due to the density gradients in the solar wind. And these counter-propagating alpha waves can shear one another and cause waves at smaller scales. So this is similar to a large eddy creating smaller eddies in fluid turbulence. So, and the magnetic field that we observe is a superposition of alpha waves over a wide range of scales, and it happens to be random, chaotic, and turbulent. But how does these turbulent fields cause heating of the solar wind? So consider a gyrating particle around a slowly varying magnetic field. Its orbit is roughly circular, but the center of the circle moves slowly. However, consider a particle gyrating around a turbulent magnetic field. Its velocity gets random kicks and its velocity takes a random walk in the plane perpendicular to the mean magnetic field. And this causes heating. So initially, if we had isotropic Maxwellian distribution, due to the stochastic heating, the distribution function diffuses to higher perpendicular velocities. And the ratio of perpendicular to parallel temperature, which is called the temperature anisotropy, increases because of stochastic heating. However, this cannot increase indefinitely. So once the anisotropy reaches a particular threshold, it creates a lot of free energy. And an instability called ion cyclotron instability kicks in. And using the free energy here, it generates a circularly polarized electromagnetic wave called ion cyclotron wave. And the wave then scatters some resonant particles and reduces this temperature anisotropy to less than a threshold value. So the instability basically constrains the deviation of thermal equilibrium of particles. However, the opposite of this instability is also possible if we have an initial more isotropic distribution of particles, and if there is an ion cyclotron wave, it can damp onto these particles and increase its anisotropy until the threshold value. So this is the opposite of instability, and it's called cyclotron heating. So now, keeping these processes in mind, what can we learn about the solar wind heating from its observations? So there is a spacecraft called Parker Solar Probe, or PSP in short, which is observing the sun at unprecedented proximity. So it is as close as 10 times the radius of the sun. So the red curves here are the latest orbits of the probe, and this is the sun, the yellow dot. So a striking feature of the probe's observation is the abundant presence of these circularly polarized ion cyclotron waves. So I show an example here. As a function of frequency and time, I plot a quantity called sigma. So sigma is the sign of the phase difference between the two magnetic field fluctuating components in the plane perpendicular to the local mean magnetic field. So if you have a circular polarization, this phase difference is plus or minus 90 degrees, and sigma is plus or minus 1. So we see this pure circular polarization at a band of frequencies closer to this proton gyration frequency, indicating the presence of these waves. And our team here at Arizona, we have statistically analyzed the probe's orbits. It has completed 24 orbits. We have identified such circularly polarized waves. And here we show the wave frequency and handedness of circular polarization as a function of time for a 10-day period around the closest approach of the probe in one of the example orbits. And the black curve here is the radial distance of the probe. And we see as the probe goes closer to the sun, the local gyration frequency increases, and accordingly, the frequency of the observed waves also increases. And the blue band here that we see are ion cyclotron waves, and we see that they occur continuously and they occur abundantly. And moving ahead, so the top panel is the same plot as before, but in the bottom panel, I show the green curve is the observed temperature anisotropy of protons, and the red curve is the instability value for instability threshold value. And we strikingly see, corresponding to this blue train of ion cyclotron waves, the green and the red curves are consistently close to one another. So what does this plot tell us about solar wind heating? So we argue that following process is occurring. So initially, suppose the proton distribution is isotropic at all radial distances. And close to the sun, the protons are anisotropically heated due to stochastic heating, and the temperature anisotropy reaches a threshold. And the instability kicks in at this point and generates a wave. And the wave propagates out for a short distance. It again encounters isotropic protons, damps onto these protons, and increases their anisotropy until it hits the threshold. And it generates another ion cyclotron wave. So this process can keep happening for higher and higher radial distances. And in this way, there can be a continuous chain of waves at all distances, and correspondingly, the temperature anisotropy is consistently at the threshold. And this is what we saw in the previous slide. Right. So basically, in this manner, these waves can mediate the radial heating of the solar wind, which we try to understand.
Well, actually, can you put the last cartoon that you showed here? So basically, here you're proposing that between the turbulent heating very close to the sun and then these waves, they have to reach a steady state.
It is kind of a steady state. The anisotropy is consistently near the threshold. So it's a kind of a steady state. It doesn't move.
And is that consistent with in the velocity plot that you had at the beginning? There was like a lot of noise and it looked like very turbulent. Like this is a steady state, but highly turbulent and supersonic states of the gas.
You mean this plot?
Yes, something like that.
So this plot it covers a really wide range of radial distances. So my work that I presented was very close to the sun. So you see until like 70 AU,
So the scale of that cartoon on this plot is
very
kind
here,
of
very close. Not even a single
basically you.
single
Okay.
thing. And also there are other processes that are happening. So this is just this is oversimplified.
Do you suspect that it might be operating out to further radii? Or is it just, are you just attempting to explain that like inner radius of the thing?
So because we use observations from this probe, the probe is very close to the sun. So we can only study the radial distances where it makes observation. Yeah, but there are other spacecraft which are at various distances and you could look into faraway distances as well.
I guess related to that, are there any theoretical considerations why they couldn't propagate out to 60 AU?
So no, the waves can propagate far, but right. So the waves, if they encounter a plasma that is isotropic, they happen to damp very quickly, right? If suppose somehow the plasma it cannot absorb any more waves, then the waves can propagate far, but it doesn't happen. So usually the wave finds an isotropic distribution soon and it damps. Yeah, so a single wave usually does not propagate very long, which we also see in the frequency. So when a wave propagates far and it is dispersive, this wave is dispersive, so the frequency band can become wide, but we don't see that the frequency band is compact. So we assume that they don't propagate far until 60 AU. But waves can be generated at 60 AU and propagate a little bit over there. You know, they can be there as well.
In interest of time, let's thank our speaker again. Is D1. I'll let you when you're 5 minutes in.
And if all the speakers could just come to the front after this talk, let's take a quick picture.
Wait. Yes, there should be.
Okay. So hi everyone. My name is Niranjana. I'm a third-year grad student at Astronomy department. And I'm working with my professor, my professor, Dr. C.K. Chan. And today I want to talk about our research work, focusing on the stability analysis of fluid discontinuity profile and its application to the destruction of flux tube within the magnetically arrested disk. So first, I want to show you why we're interested in magnetically arrested disk or MAD disk and the flux tube. So here are some fancy simulations. Magnetically arrested disks are strongly magnetized accretion state around supermassive black holes. It has gained interest mainly because of the Event Horizon Telescope observations. So the EHT observes both Sagittarius A star and M87 stars. Their observations are consistent with the MAD model accretion for the accretion disk around these two supermassive black holes. And as you can see that on the left-hand side, the simulation shows the quasi-periodic flux eruption events where you have a very low density region being expelled from the event horizon. That's what we call the flux tube. And on the right-hand side is a flat space simulation for Sagittarius A star, which is consistent with the MAD model. So that's a MAD disk, and here is a 3D magnetic field structure for the flux tube. As you can see, it's mainly dominated by the vertical field surrounding the midplane. On the other hand side, if you look at the other parts of the disk, it's mainly the azimuthal field. So there is a rotating magnetic field in this case. Why we are interested in the destruction of the flux tube? So in a recent simulation resolution analysis of the MAD simulations, people found that as resolution become finer from a very low resolution case to a very much higher resolution case, it shows signature of fluid instability is happening as an interface between the flux tube and the disk. But however, there's no pinned down physical mechanism that can explain this phenomena and why we don't see the destruction or the fluid instability in the low resolution simulations. So in our work, we start from the first principle MHD equations and using linear mode analysis try to solve these problems. So first, I want to go through some math in just one slide. So we start with a classic Kelvin-Helmholtz instability, where you have a discontinuous density profile and also velocity profile. We analyze this by linear mode analysis. So you start with ideal MHD equations with just gravitational source term. You can write them in a compact conserved form, and then you add the perturbation to the steady state, linearize the system, and in the end, you can write this linearized system into a compact eigenvalue problem, where the lambda and q are the eigenvalue and eigenvectors of this system. Solving this eigenvalue problem tells you the eigenvalue lambda that governs the temporal evolution of your perturbation, while the eigenvector q will tells you how well the perturbation grows in the spatial directions. And so in the end, you combine these eigenvalue equations with appropriate boundary conditions and the jump conditions relating the upstream and downstream quantities to solve these three equations like simultaneously. In the end, you will get the dispersion relation, which tells you everything about the instability. So after solving that, you can reconstruct some quantities. Here I reconstructed the velocity field. As you can see here, is showing the vortex structures, which is a signature of Kelvin-Helmholtz instability in the fully nonlinear simulations. So I just want to emphasize that with linear mode analysis, we can understand a lot about the instability. So then we are ready to apply this framework to the mad disk. So with a mad disk, we are now adding more ingredients into this framework. As I mentioned, there is a rotation of magnetic fields between the flux tube and the disk. So you have magnetic fields, you have a shearing background, which is common to a accretion disk. And if you are doing a local analysis, as we did here, we're using shearing box approximation. In the end, you will get a linear velocity profile rather than just a constant velocity profile. Since we're want to explain what we saw from the simulations, and simulation itself is fully compressible, so you need to add compressibility here, which makes the equations very complicated and hard to solve analytically. So in the end, we use pseudo-spectral method to solve that differential equations and use a minimization algorithm to identify possible modes. So here I'm going to show you some preliminary results. Here we did a calculation for two configurations where the blue is a small velocity shear, while the right is a larger velocity shear. And we define growth rates gamma, which is a real part of lambda. So positive gamma corresponding to exponential growth, meaning your configuration is unstable, while negative gamma corresponding to exponential decay, and you have a stable configuration. So as you can see, the larger velocity shear on the right text always corresponding to a larger perturbation, which is a strong evidence showing that instability is likely driven by the energy stored in the shear layer and the discontinuity. And we can also compare the eigenfunctions. As you can see here, as the wave number, its magnitude increases, the eigenfunctions become steeper from the orange to green and from orange to purple and green. So eigenfunctions become steeper, which means more power is stored near the discontinuity, which is also consistent with the Kelvin-Helmholtz type instability. And also, as the wave number increases, this corresponding to small or short wavelength perturbations. So we are more likely to observe small scale perturbations. And let me connect back to the simulations here. In the low resolution simulations, we don't see the signature of fluid instability, and our theory can naturally explain this because it doesn't have enough resolution power to resolve the small scale perturbations, which will make the simulations to be stable. And I also reconstruct the velocity field. So here's a very short movie showing the evolution of the velocity field. As you can see here, it also shows vortex-like structures being developed, which is also consistent with our initial guesses that Kelvin-Helmholtz or velocity shear can destruct the flux tube. So just want to leave the conclusion slides here. We conduct the first analytic study of the flux tube and these interface within the mat, and our results imply the velocity shear can destruct the flux tube. And happy to take questions. Thank you.
This is really interesting work. So you mentioned that the velocity shear can disrupt the flux tube. What conditions do you have to place on the density? Like, does a more dense boundary or less dense boundary like help preserve the structure? Flux tube?
Yeah, so what I'm saying is Kelvin handles, it also hiddenly involve a radiator there. So you have a density contrast between these two layers. So for people who don't know, like radiator means you have a heavier fluid on top of a lighter fluid. So this configuration is naturally unstable. So to answer your question, if the density contrast becomes larger, it will naturally become more likely to be unstable. So here I think we are still working on to explore more parameter space to see is the velocity shear like the so here in the previous results I just show you the comparison between two velocity shears. But we can do like things like two density contrast and to see which one is like more impactful for the results.
I have one question. If you have the effect of the instabilities of on the magnetic field profile in disk, but do you have in the two simulations, the under-resolved one and the one that actually shows the growth of the small scale instabilities, do you get a final magnetic field that is different?
Yeah, so fortunately that simulations wasn't run by myself, so I don't have that access for the magnetic field configurations. But that's kind of like the next step. So in our own simulations, we are running a low resolution simulation. We didn't see the destruction of the fluid instability happening there. So the vertical field will stay there for a very long time.
Yeah.
So yeah.
I wonder if that statement would remain true if you had more resolving the instabilities.
Yeah, so I was trying to reconstruct the velocity field pattern, like its evolution, similar to the velocity field evolution, and hopefully I can compare them to their simulations.
One last question.
So if you scale down the problem in mass, so like will these magnetically arrested disks also be easy to form in stellar mass black holes? And can we learn something from the observations of Cygnus X1, say?
Yeah, I do think because the GRMHD simulations we're running is mass-free, so we can definitely scale down to stellar mass black holes. And I think there are also people doing the simulations around protoplanetary disk, also showing the magnetic fields evolutions here. So this so this work, even though we are focusing on supermassive black hole accretion disks, but it can be applied to other scenarios as well.
Okay. And let's thank Niranjana again. And you guys go here, you need to take a picture. So don't run away.